Only the thing is the change in potential energy will occur because it is due to position, as I told. Torricelli discovered that speed of a flux from an open tank, and it is given by a formula which is identical to that of freely falling body. We know what is Bernoulli's principle. It is a sum of pressure, potential energy per unit volume, kinetic energy per unit volume is always constant. Since there is a pressure exerted by the atmosphere, the pressure at point 2 will also become PA. Hello everyone, welcome to session 3 of chapter 10, Mechanical Properties of Fluids. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. In the last session, we had discussed about Pascal's law. What is Pascal's law? What are its applications? So, the applications of Pascal's law are hydraulic lifts and hydraulic brakes is what we discussed in the last session. And we have also studied about the nature of flow of fluids, where the flow of fluids is classified into a streamlined flow and turbulent flow. What are the characteristics of streamlined flow and what are the characteristics of turbulent flow? We have discussed in the last class. We have even discussed about equation of continuity of the motion of a liquid or the fluid, and it is given by AV is equal to constant, where A is a area and V is a velocity. Or we can also write it as A1 V1 is equal to A2 V2 for a different cross-sectional area of a pipe in which the liquid or the fluid is moving. In today's session, we are going to discuss about one more important law in the study of mechanical properties of fluids, that is the Bernoulli's principle. What is Bernoulli's principle? What are its applications? What does it state? So, it is very important according to examination point of view. So, let us see what is the statement of Bernoulli's principle. It states that for a streamlined flow of an incompressible non-viscous fluid, generally it is an ideal fluid, incompressible non-viscous fluid, the sum of three terms we need to remember here: the pressure, potential energy per unit volume and kinetic energy per unit volume at any part remains constant. I repeat, the statement of Bernoulli's principle is, it is nothing but for an incompressible non-viscous fluid for a streamlined flow, the sum of pressure, potential energy per unit volume, kinetic energy per unit volume remains constant at any part of a fluid when we consider when it is in a streamlined flow. So, it is given by the expression P plus rho GH plus half rho V square is equal to constant, where P is the pressure. So, how is this rho GH? How do we get this? We know potential energy is given by the expression mgh. Now, we are saying that the potential energy per unit volume, which means divided by V. Here we have m divided by V. M divided by V is nothing but mass per unit volume, which is nothing but the density, and it is given by the symbol rho, and hence we get rho GH. Similarly, kinetic energy expression is half mv square. Here we are saying that kinetic energy per unit volume, and hence we can write this as half m divided by V into V square. So, we get m divided by V. Here we are no need to cancel this V term because we know mass by volume is nothing but density, and this is given by a symbol rho, and hence the equation we get half rho V square. So, this says for an incompressible non-viscous fluid in a streamlined flow, the sum of, here you can see the plus sign, the sum of pressure, P stands for pressure, rho GH is nothing but potential energy per unit volume, plus half rho V square is nothing but kinetic energy per unit volume remains constant. So, by remembering this expression, you can write easily the statement of Bernoulli's principle. So, this can also be written as, suppose if we take the pipe of different cross-sectional area, you can observe here this area of cross-section I have considered as A1, and here the area of cross-section is considered as A2, and the pressure of the liquid while entering the pipe is P1 and pressure at this end is P2. Suppose let us consider this pipe is located with variable height, which means the height where the liquid is entering the pipe is H1, and here the height is H2 where the liquid will exit from the pipe. You can observe the varying heights here, and here also I have considered the pipe with different cross-sectional area. In this case, how to write the Bernoulli's statement? So let us now write the Bernoulli's principle at one end, then we will equate with the other end. Since it says that the sum of all these three variables remains constant at any part. So we can write, so at one end we are writing now the pressure is considered as P1 and half rho V1 square, the kinetic energy of a flowing liquid. Here the velocity of the liquid while entering is V1. So kinetic energy is given by half rho V1 square plus here the height is considered as potential energy is nothing but the energy due to its position. So the height of the pipe is located or the position is at H1. So we will get rho g H1 because we know rho gh is nothing but the potential energy and the H here we have considered is height H1. So it is rho g H1 which is equal to the pressure at this end is P2 plus the kinetic energy while the liquid getting exit from the pipe is half rho V2 square, where V2 is the velocity of the liquid while it is coming out of the pipe, and rho g H2 is nothing but the position here, which is nothing but the potential energy. H2 is nothing but height of the pipe where it is located. So rho g H2 gives the potential energy. From these two we can say that the sum of pressure, kinetic energy per unit volume, potential energy per unit volume, which remains constant at any part. So this is Bernoulli's principle. So what if the pipe is at same height? What if we consider a horizontal pipe where both the heights are same while liquid entering and coming out? So what happens to the expression? Let us see it now. So it is P1 plus half rho V1 square as it is kinetic energy term, and only the thing is the change in potential energy will occur because it is due to position as I told. So when the heights are equal, so both this is H1 from the ground and this will also be with the same height, which means this is also H1. So now the expression becomes half rho V1 square plus rho g H1, which is equal to P2 plus half rho V2 square plus rho g H1 only, because we are saying that the horizontal pipe which is located at the same height from the ground. Now we can cancel these two terms and we remain with P1 plus half rho V1 square, which is equal to P2 plus half rho V2 square. This is called as Bernoulli's principle. There are various applications of this Bernoulli's principle which we are going to discuss in our upcoming slides. Now before that, let us now know about one more important law called as Torricelli's law. So it is also called as speed of efflux. What do you mean by efflux? The word efflux means the fluid outflow. What is this fluid outflow? Where do we come across all these? We might have all observed that the water is coming out of the tank when it is completely filled. Like if you have a small opening here, how the water will come? What is the speed of this fluid outflow? And this fluid outflow from a hole, and that is called as efflux. So here we are going to measure the speed of efflux. What is the meaning of efflux? Efflux is nothing but fluid outflow, and this speed of efflux is given by a person called Torricelli, and hence it is named as Torricelli's law. So let us know about this more. The word efflux means fluid outflow. Torricelli discovered that speed of efflux from an open tank, and it is given by a formula which is identical to that of freely falling body. Why it is called as identical that of freely falling body? When the water is coming out of an open tank, the speed what the water comes out will be almost equivalent to a freely falling body. It is similar to the freely falling body, and it is discovered by a person called Torricelli. Then what is the expression? Let us now derive it. So consider a tank containing a liquid of density rho. It is not P, it is a density symbol that is given by rho. So let us consider a tank which is contained with a liquid of density rho and which has a small hole in its side at a height of y1 from the bottom. So this is a tank what we have considered. It has a small hole here, and that is at a height of y1 from the ground. So this is the height. The height is y1 from the ground. Here now we are going to derive the speed of the outflow of fluid. The air above the liquid is at a height y2 and it is having a pressure P. So it is y2. Here we can see the air above the liquid. What is the height where the air is present? That is at y2 from the ground and it is having a pressure P. Next, from the equation of continuity, what is the equation of continuity? It is AB is equal to constant. What is A? A stands for area of cross section and V is velocity. So we have an equation A1 V1 is equal to A2 V2. Here we have liquid which is at rest and from the hole when the liquid flows, it flows with the velocity V1. So from equation of continuity we can write A1 V1 is equal to A2 V2, or from this we can write V2 is equal to A1 divided by A2 into V1. We will use this for further simplification. So this is from equation of continuity. I hope the diagram is clear to everybody. Here there is a tank which is having a small hole outside where the liquid flows when it is completely filled, and this flows with a velocity V1, and here the pressure will also be there and that is called as atmospheric pressure. Because there is a hole, atmosphere exerts a pressure on the water and that is given by PA. And it stands for atmospheric pressure. And here when the fluid is at rest, there is an air gap and this air is present at a height y2 from the ground and the pressure here at the top surface is P. This is about the diagram. According to this, now we are going to derive the expression for speed of efflux. So if the cross-sectional area of the tank is much greater than that of hole, then we may take that the fluid at the top approximately is at rest. According to our equation of continuity, this area and velocity are inversely proportional to each other. So here the cross-sectional area of the tank when compared to this hole is greater. So when the area is greater, velocity must be lesser according to equation of continuity, because we know area and velocity are inversely proportional to each other. Now the area is greater, which means velocity is less and it is almost equal to 0. So when you compare to this hole's area of cross section, the cross sectional area of the tank is much bigger, and hence at the top even there is a velocity, because if the water decreases there will be some motion, even there is a velocity, but when the area is larger when compared to the hole, the velocity is very smaller and is almost equal to 0, and hence we may take that the fluid at the top is approximately at rest. It is approximately at rest. That is, if A2 is greater than A1, this is the area of cross section of the tank and this is area of cross section of the hole. So area of cross section of the tank is very much greater than area of cross section of the hole, which means the velocity here, that means at the surface, top surface, will be very much lesser than the velocity at the hole where the liquid is going out. And since the velocity is very much lesser, it is said that at the top the fluid is approximately at rest. Now applying Bernoulli's equation at point 1 and point 2, what do we get? We know what is Bernoulli's principle. It is a sum of pressure, potential energy per unit volume, kinetic energy per unit volume is always constant. Now we have 2 points. At point 1 is nothing but the place where we are talking about the hole, and point 2 is nothing but the fluid at rest inside the tank. So now let us apply this Bernoulli's principle at both the points. So here one thing we have to observe is, first point is nothing but at the hole. So at the hole the pressure is nothing but atmospheric pressure and that is given by PA, and at this second point the pressure of the liquid is given by P. Now according to this, let us now write the expression for Bernoulli's principle. For point 1, pressure is given by PA. We know sum of pressure plus potential energy plus kinetic energy is constant. So here P stands for pressure, and at point 1 the pressure is atmospheric pressure. So, Pa plus half rho V1 square, that's kinetic energy per unit volume, plus rho g Y1, because in the previous Bernoulli's principle expression we have taken rho g H1 because H was the height what we have considered. In this example the height what we have considered is Y1 because at Y1 height the hole is present, and hence we are writing the expression now for point 1, and hence it is rho g Y1, which is equivalent to, and the pressure at the second point is P plus, here we have told that the velocity is almost equal to 0. So, half rho V2 square term becomes 0. Why? Because V2 is 0. The velocity at this surface is 0. Hence, V2 is 0. Since V2 is 0, this half rho V2 square entire term becomes 0, and hence we have not mentioned here. So, pressure P plus rho g Y2. Y2 is nothing but the height of the liquid till this top surface from the ground. So, the Bernoulli's equation is P plus rho g Y2. Since the velocity at this point is 0, there is no kinetic energy term. Now, this expression can be written as Pa plus half rho V1 square is equal to P plus rho g into Y2 minus Y1. So, how did we get this? So, go to the last expression, that is Pa plus half rho V1 square plus rho g Y1 we have here and rho g Y2 we have here. Take this to the other side. So, what do we get? We get Pa plus half rho V1 square is equal to P plus rho g Y2, already we have here, and this plus rho g Y1 when it goes to the other side becomes minus rho g Y1. Now, from these two we can take rho g common and we can write Y2 minus Y1. You can observe here, this is Y2 and this is Y1. So, Y2 minus Y1 gives us H. So, now Y2 minus Y1 can be substituted by the letter H, and that is how we get Pa plus half rho V1 square is equal to P plus rho G H. Now, simplifying this further, we can write half rho V1 square is equal to, take Pa to the other side, that is P minus Pa plus rho G H. We need speed of efflux. In this term, in this entire expression, the speed is given by a letter V. So, let us now retain V to one side and let us bring the other terms to the other side. So, V1 square is equal to, this 2 gets cross multiply here. So, we get V1 square is equal to 2 into P minus Pa plus rho G H divided by rho, because here we have rho, this is multiplied with V1, when it comes to the other side it will come to the denominator. So, now let us simplify this. So, we get 2 into P minus Pa divided by rho plus 2 into rho GH divided by rho. Now, we can cancel this rho and we remain with 2GH, that is 2GH plus 2 into P minus Pa divided by rho. Now, we need just the velocity term, but we have V1 square here. So, let us now write it as V1 is equal to square root of 2GH plus 2 into P minus Pa divided by rho. Now, this is the velocity expression. Let us now imagine if this is a open tank. If this is not a closed tank, if this is open tank, here also the atmosphere will exert some pressure. Since there is a pressure exerted by the atmosphere, the pressure at point 2 will also become Pa. Because the tank is open, the atmosphere will also exert some force on the fluid. So, the pressure is considered as Pa. If it is an open tank, the pressure at point 2 is also considered as Pa. Then what happens to this expression? So, this expression becomes V1 is equal to square root of 2GH plus 2 into, here P will also become Pa if it is an open tank, Pa minus Pa divided by rho, and this gives us square root of 2GH plus 2 into Pa minus Pa is 0 divided by rho, which is equal to square root of 2GH plus 2 into 0 is 0. 0 divided by anything is 0. And we get just root of 2GH is the expression for speed of a freely falling body, which is also an expression for speed of efflux. And this is known as Torricelli's law. So, in today's session, we have discussed about Bernoulli's principle, what is the expression for Bernoulli's principle, and the speed of efflux, that is Torricelli's law. So, in the upcoming sessions, let us discuss about the applications of Bernoulli's principle, which is really interesting. Until then, take care all of you. Thank you.